Okay, so can anybody remind me of what we're doing?
We just started Fourier analysis on finite abelian groups.
Okay, Fourier analysis on finite abelian groups. Yeah. And what are we trying to do? Abelian groups.
This time we kind of went over a bunch of definitions.
Okay, yeah. What kind of definitions? So right,
Like
so you have some finite abelian group. Right, and there's right. What's the goal? Right? Can anybody tell me what the goal is?
We want to find an orthonormal basis for V.
Exactly. Right. So we're looking at V. Right. So V is the functions on the group in bit C. Right. And this is a order of G dimensional space. Right. And we want an orthonormal basis for V. Right, so that we can do the Fourier analysis. Right, basically Fourier analysis is just like linear algebra. Once we have the orthonormal basis, then we can do the inversion. Right, the inversion is basically just a statement about orthonormal bases. We can get Parsifal's theorem, Plancherel's theorem, which is just Parsifal's theorem. Okay. So, right, we want an orthonormal basis, and remember what we were doing. We looked at these things called characters, right? Right. The thing that was going to work out for us were the things called characters, right? They were homomorphisms from G into the group, into the circle group, right? So homomorphism. Homomorphisms into there, and we saw that that these guys were actually orthogonal, right? No, in fact, orthonormal, right? Right. We saw that all of these guys had no, we hadn't seen that yet. Sorry. What we had done was we had defined the characters, and then said let's let G hat denote the collection of all characters, and then we put on a group law. So G hat plus the group law became something that we called the dual group, right? So we defined a way of multiplying characters, kind of the obvious way of multiplying characters, and then we defined this thing called the dual group. And then the last thing we did was we showed this lemma that said that to show that something is a character, you didn't have to, as long as you had a function that went from G into C, excluding 0, and the function was multiplicative, then it was going to be a homomorphism. So then it was going to be, then it was going to be a character. In other words, it was forced to be into the circle rather than into the non-zero complex plane, right? That's where we finished up. That to show something as a character, we just had to show that it didn't vanish, and that it was multiplicative, right? That it respected the group law. Okay, so now today we're going to show that the characters are what we want. The characters are what we want. Okay, so again, let's recall the space V, right? So that's the space of functions, functions on G, complex value functions on G. And we define an inner product, F comma G, in the usual way, right? We're going to take So we're gonna define the inner product in the usual way. Well, what's the usual way? What are we gonna? How are we gonna define
It's like
it?
f g times g bar.
F times g bar as you sum over all elements of the group. Okay, so our first goal is to show that all the characters are orthonormal. Okay, so the first thing we're gonna use is the lemma. The first thing we're gonna do is go for this lemma that says that if E in G hat is a non-trivial character, then the sum over all values is 0. Okay, so the way you want to think about this is that this is like a cancellation condition, right? Remember back when we were doing Fourier analysis on the circle, right? You know, the integrals of our characters were all 0, except for the trivial character whose integral was 1, or 1 or 2. I mean 2 pi, right? So this is basically like a cancellation condition. Okay. And the proof is pretty simple. You say, well, consider this sum, right? Consider this this integral, right? And then we know that since E is non-trivial, we know that there exists some point B in the set where E of B is not 1. Okay, so multiply it by that. So then E of B times summation E of A through A sums over G. Well, that's going to be, we can move that in. We get E of B, E of A as A sums over G. But since E is a character, we can put them together, right? We use the multiplicativity. We get E of BA as A ranges over G. Right? But multiplying by B just permutes the elements of G, right? Multiplying by B just permutes the elements of G, and so this is the same thing as taking the sum over all elements. Again, right? And so what does that tell you? That tells you that E of B times this thing, E of B, which is not equal to 1, times this thing equals that thing, right? And so you see that the sum must be 0. Right. Okay, so that's the first thing, right? And now we want to show that that in fact that we want to show that that G is an orthonormal family. So here G is an orthonormal So, okay, so yeah, so there's two parts to that, right? First off, we want to show that whenever you take for any E and G hat, the inner product of itself, the inner product against itself is 1, right? Okay, but that's basically just a calculation. You say, well, E of A, multiplied by E of A bar as A ranges over G. So the, oh, I'm sorry. This, when I wrote down the inner product,
Oversized.
yeah, I forgot you have to divide by the order of G. Okay. So the inner product is going to be, right, it's going to be whatever the side is G times the sum, right? But this is just, of course, 1 over the order of G times the norm of E of A squared, right? Right, because that's what this is, right? You take something times its complex conjugate. That's the modulus squared, right? And remember that E was a map into the circle group, right? So these are all size 1, and so you get the order of G over the order of G, which is 1. Okay, so that's part 1. In part 2, we want to show that for E, if you have two different characters, we want to show that if you have 2 different characters, then the inner product is 0. Okay. So you say, okay, well, let's look at that. Let's look at that inner product, right? E against E prime. Well, that's going to be 1 over absolute value G summation E of A, E prime of A, E prime of A bar. Right. Right. Okay. But that is the same thing as that's the same. E prime bar is the same thing as E prime inverse of A. Right, because when you multiply on both sides by E prime, well, you're going to get 1. Right, so what you get here is 1 over the order of G, E of A, E prime inverse of A, as A ranges over G, right? But that is the same thing as 1 over the order of G times E times E prime inverse evaluated of A as A ranges over G, right? Using the group law. Right? Is that okay? Right. Okay. So right now E is not equal to E prime. So this is a non-trivial character. And what we're doing here is taking the sum over a non-trivial character, which we just showed is going to be 0. Okay, so these are just sort of like simple calculational things. Okay. So what we have right now is that we're trying to get an orthonormal basis. We're trying to get an orthonormal basis for vector space V, and what we're seeing is that if we have a sufficient number of characters, then we're done, right? These guys are orthonormal. So what we're hoping, right, our goal, our next goal, is to show that the size of G is the same thing as the size of, the size of G hat is the same thing as the size of G, right? Because then we have our orthonormal family. Okay. Okay. So okay. So yeah, right. I'm gonna erase this. Okay, so right, so we want to show that our goal is to get this theorem that G is a finite abelian group. Then G hat is a basis for V. Okay, and the way we're going to do it is going to involve some linear algebra. This is going to be kind of fun. Okay, so some linear algebra, some useful linear algebra. Okay, so definition. Right, you have. Sorry, it's getting old. Can't read. Why did I print this out in small font? Let V be a d-dimensional vector space, and T from V to V be a linear transformation. I'm sorry, d-dimensional inner product space. Okay. And you have a linear transformation. So I'm gonna define what unitary operators are. Who remembers what unitary operators are? Kai, go ahead.
They preserve like the norm.
Yeah.
And then the result in
Or
T inverse.
Yeah,
itself, if it's adjoint is equal to
equivalently,
yeah.
yes. So like TV, TW, inner product is the same thing as VW.
Yep.
Right? It preserves the angle in some sense. Okay. Okay. So unitary operators, and then we're gonna use the spectral theorem. I don't know did you guys see the spectral theorem when you guys did linear algebra? No.
Which one are you thinking of?
For unitary operators. So
The diagonalize.
yeah, that it's diagonalizable. Yeah, that's so.
Over C.
That's
Yeah.
what we have to use in our homework, right?
But you only need that they're normal, right? Like you only need normal to diagonal.
That's true. That's
Okay.
true. Yeah. Yeah. So given any unitary transformation, there exists a basis V1 to VD, so of V of eigenvectors of T. Okay. In other words, the transformation is diagonalizable. Okay. So now I realize that I should not have started here. Should have trusted my gut. Okay. So now we're going to go for this thing, which you can call simultaneous diagonalization. And you didn't take linear algebra with me, did you?
No.
Okay, sorry. Okay. So let V be a finite dimensional inner product space, of course. Inner product space. And suppose you have a bunch of linear transformations, a family of linear transformations. Okay. Sorry, these should be unitary, of course. Unitary linear transformations. If all the ti commute, right, doesn't matter in which order you take them, then there exists a basis of V consisting of eigenvectors for every ti. Okay, so the eigenvectors are eigenvectors for every element of the family, every member of the family. Okay, right. In other words, there is a basis of eigenvectors with respect to which all of these guys are diagonal, as long as they commute with each other. Okay. The proof is by induction. The base case is obvious. The base case is the spectral theorem, right? It commutes with, there's just one of them. You don't have to worry about it. So now let's suppose that it's true. Suppose the lemma is true for any family of k minus 1 commuting unitary transformations. Okay. So now, now suppose we have some family, T1 through Tk. Right. So suppose we have a family of k such transformations. Well, the spectral theorem says that we can write V as a direct sum V lambda 1 plus V lambda 2 plus V lambda k, no, S. We can write V as a direct sum of eigenspaces of Tk. Okay, of the last guy. Okay. Right. That right, that's what the spectral, that's what diagonalization means, right? That you can break up your space into a direct sum of these eigenspaces. Okay, so now observe, right? For any guy before that, so j between k minus 1 and 1, we see that if V is if you take some vector in the eigenspace, right? You take some vector in any one of those eigenspaces, right, and apply apply Tj to it. Okay, apply Tj to it, followed by Tk. Okay, well, commutation says that this is going to be Tk of this is going to be Tj of Tk of V, right? But that's going to give us Tj lambda I of V, which is just lambda I Tjv. Right? Okay, what's the point? The point is that Tk of this thing is just lambda times that thing, right? In other words, Tj preserves the eigenspace, right? Anybody in the eigenspace, you hit it with one of the other guys, well, it's still going to be in that eigenspace. Okay, so the behavior, right? We don't have to worry about when we look at Tj's behavior on V, right? Each of these components is invariant under the earlier guys. Okay, so is that okay?
Sorry.
Yeah.
Sorry, why do we know that DJV is in the eigenspace?
TJV, well, so right, this is the eigenspace for TK, right? This is TK's eigenspace, and you see that
When you apply TK to that thing, it scales up by the right length.
Yeah.
So it has to be in the eigenspace.
right? So if you take anybody in the eigenspace and you hit it with TK, well, it's still in TK's eigenspace, right? Right? It still gets scaled by that eigenvalue.
But that's DK's eigenspace. So
Yeah.
why is DJ of V in that?
All I'm saying is that TJ maps things in here to things in here. Right? If you start off with somebody in the eigenspace, you take TJ of it, it's still an eigenvector of TK with eigenvalue lambda I.
Okay.
Yeah. Okay. 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 So the point is that we can consider each of those eigenspaces independently, right? We think of those, right, so for each subspace, each of those eigenspaces, V sub lambda I, if we now look at the family, but not including T sub k, right? These guys, just act within the subspace, and so we can apply the lemma to this case, right? We've got a vector space, and we've got these operators. They commute with each other, and there's k minus one of them. Okay, so can be simultaneously diagonalized. Right? That is that each of these guys in turn can be broken into a direct sum of smaller subspaces, on each of which each of which is an eigenspace for all of these guys. Right? Okay. So right. So each v lambda I can be expressed can be decomposed into a direct sum of subspaces which are each eigenspaces for all T1 through tk minus 1, right? Right? But, you know, those are all contained, right? So we'll have eigenvector bases that that work for all of these guys, right? But those are all contained within within v lambda I, right? So those eigenvector bases are also eigenvector bases for tk. So the eigenspace for T sub k, right? So we have a decomposition into eigenspaces for everybody. Okay, so that's it. Okay, and the construction of the construction of the orthonormal basis for V, you know, when we go back to the you know, to the dual space, when we're trying to show that the dual space is an orthonormal basis. You know, I'm sorry, what did I say? When we try to show that that the characters form an orthonormal basis, we can form an orthonormal basis of characters. We'll use exactly we'll use exactly this. Sorry, let me just show you. I'm not saying things clearly, but in any case, is this clear? Okay, this is pretty cool. Yeah. Okay. So now let's do it. Hang on.
We didn't use unitary anywhere in here, right? So this is true for just normal operators as well.
Well, we needed to use the spectral theorem in the very first case, right?
Yes.
To show that.
Yes, which
Right.
holds for normal operators.
Oh, I see what you mean. Like,
Yeah,
so
I was
if
just
we.
curious, like if the induction step holds in general, then we could do this for any. Yeah. Okay.
Yeah.
Yeah.
Yeah, as long as they commute.
Huh? Yeah. Oh, as long as they commute. Right.
I meant as long as it diagonalizes,
Yeah.
Which is
Yes.
what normal is over C.
Yes.
Yeah.
Yes. True.
Okay. Cool.
Yes. Okay. Okay. So so now let's do it. This is the. I think we can do it. Okay. Here's the theorem. Okay.
Bless you.
Thank you.
Okay. So here's the theorem. Given G a finite abelian group, we can construct an orthonormal basis of characters for the functions for the vector space of functions on G. Somebody have a copy of the book? I want to check something. I'm sorry. Sorry. No,
Forgot mine.
that's okay.
I have a PDF.
Sorry. Thank you.
Oh, okay. I also have pirated.
Yes, sir.
It's like this weird word on the top of my book.
The iBook group.
Yeah. I don't know what that means.
That's where it was once pirated from.
Oh,
That's where it was once pirated. It's a server, right? I'm pretty sure.
I have no clue.
I
It's
think-
been a while since I.
I'm pretty sure iBook group is a server.
Okay.
Okay. So yeah. So that. Yeah. So sorry. G hat. Yeah. G hat is an orthonormal basis for the vector space of functions. G. Okay. So right. So okay. So remember that it suffices to show that that we have sufficient number of characters, right? That the number of characters actually equals the order of the group, right? Because we saw earlier that these guys were orthonormal, so as long as we have enough, then we're good. Okay. Okay. So. Okay, so here's the idea. Here's the idea. For each A and G, define T sub A, and this is going to be an operator from V to V. Okay, and what it's going to do is just going to left multiply the input by A. Okay, so it just shifts the it just translates the thing by A, or multiplies it by A. Okay. Okay, so then we've got this family. We have this family of TA for A and G. Okay. Okay, why do we care? Why these T sub A, right? Well, if you think, what's a character? Right? We're trying to get a sufficient number of characters. Well, for chi to be a character, chi AX, right? It has to be multiplicative. So chi AX must be chi A chi X, right? Right? Chi character, then this is true, right? But if we write that in terms of the T sub A's, what that says is T sub A of T sub A chi X must be chi A chi X, right? right? So just writing this property of characters in terms of the linear transformation, this is what it says, right? But that means that that chi is an eigenvector or eigenfunction, right? Eigenfunction, eigenvector, right? Whatever you want to call it, of T sub A, with eigenvalue chi A, right? Right. So for something to be a character, this has to be true for all A and G, right? And so you see that what it'd be very useful to get to find a character. What we're looking for are things that are eigenfunctions, that are eigenvectors for all of the TA, right? And that's exactly what we were doing with the simultaneous diagonalization. Okay, so that's why we're considering this family. Okay. We do have to observe that so we want to apply simultaneous diagonalization to this family. Okay. So you do have to observe that the TA are that the TA are unitary. So TAF against TAG, right? Well, it's just a calculation. You get summation TAF TAFB TAGB bar as B ranges over G. Right. But that's just 1 over the size of G times FAB GAB bar, right, as B ranges over G, right? But again, like we said last time, this is just a permutation, right? And so you get 1 over G summation FB GB bar, which is just F against G. Okay, so that's just a calculation. So they are unitary operators. Okay. Since they're unitary, we know that we've got the eigenvector basis for everybody, right? So there exists a basis V sub B of eigenvectors for all TA, right? For all the TA. Okay, and right. So that's a basis. That's a basis of V. That's a basis of V, and so if these guys were the characters, right? If these guys are characters, then we're done, right? Because then we've got order G. We'd have order G characters, and that's what we're trying to show. Okay, so they're not exactly characters. So if unfortunately they're not exactly characters, but we can fix them up. Okay, the trouble is that to make them characters, we need to normalize the trouble is that V of B of 0, V of B of of the identity, so let U be the identity of G. The trouble is that this might not be 1. So you just normalize. You say let W sub B of x be defined as V sub B of x over V sub B of V sub B of U. Okay, and that will get rid of that problem. Okay, and then once we do that, we'll get that these guys actually are the characters. Okay, so claim the WB are characters. Proof. Okay, so first observe that V of U, so let V be one of the V sub B, and W be W sub B. Okay. So first observe that V of U cannot be 0. Okay. The reason is, of course, would be that if for then V of anything would be TA of V of U, which would be just the eigenvalue times V of U, which would be 0. Which would mean that that your function was 0 everywhere. Okay, so that's not possible. Okay. Similarly, if VA equals 0, then if VA equals 0, then VU would be V A inverse A, which is lambda A inverse VA, which would be 0. And again, V would be 0 everywhere. Okay. So the point is that V cannot vanish. V cannot vanish, and neither can W. Okay. Okay. So so what we have is we have all these guys, right? And they are they're maps, right? So we have all the VAs are maps from G into the complex numbers excluding 0, right? And so I'm sorry, the WAs are all maps into the complex plane excluding 0. So by the previous lemma, it suffices to show that they're multiplicative. Right? It suffices to show they're multiplicative. Because remember we showed that as long as they're multiplicative and they go into and they don't vanish, then they're going to be characters, right? Okay. Okay. But we basically constructed them. We basically constructed them to be multiplicative by forcing them to be by construction they're eigenvectors of this family, And that will be enough to show that they're multiplicative, right? So you say, well, right, they are. Well, they are. Because if you look at W of A times B, well, that is, by definition, V of A times B normalized. Right? Well, that's the same thing as T sub A of V over V VU. Right? Which is the same thing as TA TB of V of U over V of U. Right, by definition. Right. But remember, V is an eigenvector for each of these guys. Right? So this is just going to be lambda B times lambda lambda A lambda B times VU over VU, which is 1. Right? This is the point, right? That these guys were eigenfunctions for this particular family. Right? But that's the same thing as, I don't know, maybe this is kind of spelling it out too much, but TAVU over VU times TBVU over VU. Right? Which is W of A times W of B. Okay, so they are multiplicative, and so they are characters, and so the orthonormal basis of eigenfunctions actually, from it we could construct, just by normalizing, an orthonormal basis of characters. Okay. Yeah. I think the main thing you want to think about is that, requiring that they all be eigenvectors of this family was exactly what we needed to ensure multiplicativity. So it was kind of the natural thing to do, right? We wanted to create characters. We created this family for which eigenvectors would basically be characters, and then we got the eigenvectors, and then we just had to fix them up a little bit, and then they turned into characters. Okay. So that's the end of the proof that the dual group is an orthonormal basis for G, and from there you automatically get Fourier inversion and the Plancherel theorem because you have an orthonormal basis. Okay, that's it.